Hello everyone, this is Jalendiran, an assistant professor working in Electrical and Electronics Engineering Department, Aliman College of Engineering, Hosur. Today we'll discuss a topic from Electric Circuit Analysis, a core paper for the electrical student in the first year. Here, active and passive elements is our topic to be discussed. And here classification of circuit elements. If you see, one of the classifications of the circuit elements is active elements and passive elements. Actually, we have some other classifications as well, but today's session we are going to discuss these two types. What is an active element? They are actually the energy sources. They are supplying either voltage or current to the circuit. The examples are generators, vacuum tubes, transistors, and so on. And certain active and passive elements connected through conductors is called active network. And if the active elements are absent in a circuit, such circuit is called passive network. Next, passive elements. These elements are either dissipate the energy in the form of heat or they may store the energy. What are the types of passive elements? The main passive elements we are going to discuss here are the resistor, inductor, and capacitor. Out of these three, resistor dissipates the energy, and inductor and capacitor store the energy, and in specific, inductor stores the energy in its magnetic field and capacitor stores the energy in its electrostatic field. Let us discuss the resistor and resistance definitions and the equations related to those passive elements. So resistor, it is an electrical element which opposes the flow of current through it. And resistance, it is a property of the material by which it opposes the flow of current through it. The symbolic representation of resistor is given here as a picture. And the symbol is R, capital R. If you apply a voltage across the resistor, we will get a current flow through this. Unit of this resistance is ohms. A relationship between voltage and current across the resistor, V is equal to I into R. This is the equation given by Ohm's law, from which we can get the equations for R and I. R is equal to V by I ohms and I is equal to V by R amperes. The power dissipates out of the resistor. Power P is equal to V into I watts, or it can be I square R, or it can be V square by R. All these equations are measured in terms of watts. And energy is the product of power and time. Power, as we know, it is V into I, or I square R, or V square by R. When it is multiplied by the time t, we get the energy equation, and it is having the unit of joules. Our next passive element is inductor, and the inductor is an electrical element which stores energy in its electromagnetic field. And the property of that material by which it stores the energy in the form of electromagnetic field is called inductance. The symbolic representation is given here in the picture. It is looking like a coil with the inductance of capital L, and we have voltage across inductor, a current flowing through this inductor. A unit of this inductance is Henry. VA relationship across the inductor. The voltage equation V is equal to L into dI by dt. it is actually emerging from V is directly proportional to the rate of change of current dI by dt. To remove that proportionality, we will be introducing a constant called inductance. In specific, it can be self-inductance. And the current voltage relationship from the basic V equation, we can have dI is equal to 1 by L into V dt. It is actually arrived from the previous equation. And we need current. So dI is integrated to get the I. So I is equal to 1 by L integral minus infinity to t V of t dt. This is current equation. So these two equations are voltage and current equations across the inductor. Similar way, we have to find how much energy is stored in the inductor. The basic equation for energy stored is W is equal to integration of P into dt, where P stands for the power delivered to the inductor, and P is equal to product of voltage into current. And here, instead of that V, we are substituting L into dI by dt, and I remains the same. This equation we are applying in the previous equation, W equation. So integral of L into dI by dt into I into dt. Dt and dt are getting cancelled as they are just change of time. So remaining we have L into integral I di. I di is integrated, we are getting I square by 2. So the final equation for energy stored in the inductor will be W is equal to 1 by 2 Li square. Our next passive element of discussion is capacitor. It is an electrical element which stores the energy in electrostatic field. The property of the material by which the element stores the energy in the form of electrostatic field is called capacitance. Here is the pictorial representation of a capacitor. The symbol is C and the unit for the capacitance is farads. And again, VA relationship across the capacitor we are discussing. First of all, let us consider the charge stored Q. That equation is Q is equal to C into V. It is actually Q is proportional to V. To remove that proportionality, we are introducing a constant called C, capacitance. And on differentiating both sides of the equation, we will get dq by dt is equal to C into du by dt. And dq by dt is actually change of charge with respect to time that results in current. So I is equal to C into du by dt. That's the current equation. And from this dV equation, we can arrive like I into 1 by C into dt. And on integrating that dV equation to get the V, we will get the voltage equation. V is equal to 1 by C integral I of t dt. And the energy stored in the capacitor, the basic equation as we discussed earlier, W is equal to integral of P dt, where P stands for the power. Power is P V into I. And here instead of I, we are substituting C into du by dt. That's the next equation. So we will get energy stored is W is equal to integration of V into C dV by dt into dt. And here on integrating dt is getting cancelled, and on integrating dV, V dV, we are getting V square by 2. So the final expression for energy stored in the capacitor is W is equal to half C V square, or in other way we can have Q square by 2C. This is the final table that represents the voltage across the resistor, inductor and capacitor, and the current equation across resistor, inductor and capacitor. Thanks for watching. We'll meet with another interesting topic soon. Thank you.